Hello, welcome to lesson 6 of our unit 2. So we're switching gears a little bit and looking at combining functions as opposed to just manipulating one function. So we're going to start with doing it graphically because I find that visually it makes it the easiest, and then we can start looking at algebraic combining of functions in our next lessons. So we'll start again with graphically. I find that this concept is a lot of fun just because it's something pretty different from anything we've done before and kind of like a puzzle trying to piece things together. So that's my predisposition as I enjoy this stuff. So hopefully you will too. So we'll start by just looking at domain and range of functions because we need to always keep that in the back of our brains. So I'm going to name these different functions. So this solid line is going to be f of x, this dotted line will be g of x, and this dashed line will be h of x, just so that I can talk about them off to the side and you're going to be able to follow along a little bit better. So I've got more room. So when I talk about domain and range, just a quick reminder that square brackets mean that those are defined points. They exist specifically on the graph, whereas when we use rounded brackets, we are dealing with things that don't actually exist. So whether it's an infinity, an asymptote, any sort of restriction where we can't actually put a specific point on our graph. So just kind of as a quick note, you are always welcome to use set notation using the squiggly brackets. Just remember that you always have to state that x is an element of the real numbers or y is an element of the real numbers before actually stating any restrictions on your domain and range. So I'll work with both here again so that you are comfortable with both, but always choose the one that's more comfortable for you. I definitely am predisposed to this, what's called an interval notation. So looking at f of x to start, and I do domain, I continue going left forever and right forever if I follow my graph. Those arrows extend in both directions. At no point do I have to stop and lift my pen. I can to keep going in perpetuity. So my domain is going to be from negative infinity to positive infinity. Okay, or just x is an element of the reals. Okay, my range, when I take my pen and I follow my graph, unfortunately I don't go downward forever. Upward, absolutely, in both directions, extends upward. But the lowest I can go on my graph if I'm following that line is at 0 and 0. So I now have a minimum, a defined minimum at 0, so that's why I use a square bracket, and I extend upward forever. So when I go to write my range in set notation, this is where things get a little bit messier. Y is still an element of the real numbers. All real numbers are used, but y has to be greater than or equal to 0. So that's what we're seeing here. So that's where set notation versus interval notation are going to vary. So I'll do g of x in just interval notation. No, I'll do both because it gets a little weird. G of x. If I look at g of x, although it's not technically drawn in, it looks very much like I have an asymptote here, and that is at x equals 2. So watch out for that. And so what we're going to be dealing with is when I follow this dotted line, I can get really, really close to 2, but not actually to 2, but I can go left forever. So my graph starts at negative infinity and extends to 2. But because I don't reach 2, I don't use that square bracket like I used up here. I'm still going to use a round bracket. Oh, I'm sorry, this is domain, not range. I'm using set notation. Again, I always start with x as an element of the real numbers, but I'm going to specifically state that x cannot be 2. Oh, and I'm not done because I went up to 2, but then I stopped. So, hold on a second here, I'm going to rewrite this below. Negative infinity to 2, rounded bracket. But my graph continues over here, and it extends upward, again approaching 2, but never reaching it from the right, but extending to positive infinity. So I use the little u to show that this is together. I'm still talking about domain. I would start at 2, rounded bracket, because we don't actually have a point there. all the way to positive infinity. Range, we're going to see something similar happen. So vertically, if I start at the bottom, I'm following this line, but again, it kind of plateaus and veers away at y equals 1. So I'm going to, but if I'd gone downward, it goes down to negative infinity. So again, rounded bracket for that implied asymptote at y equals 1. Okay, it starts up on the other side, again approaching but not actually touching 1, but extending upward to positive infinity. My set notation would be y is an element of the reals, but y cannot be 1. Finally, h of x for my domain. It has a defined point right here where my graph starts. And so even though it does have a minimum, again, and I'm using a specific value, it does have a point. So going back to kind of like what we did for our range in f of x. So I'm going to say it starts at -4, and horizontally I'm extending forever. So it goes up to positive infinity. When I write this in set notation, I'll say x is an element of the reals, and x is greater than or equal to -4. Range, again, I can't go down forever. It starts at 0 and extends upward. Though it looks like it's plateauing, it still will gradually go up forever, so it still goes to positive infinity. So my range is going to look similar to my domain, but it has to be greater than or equal to 0. So while we're working through all of our lessons, it's continuously important to remember about domain and range and where they exist and where they don't, because it will get to a point where we talk about restrictions, and we're going to see that in lesson 9 here. But we'll talk about it a little bit as we continue through. But our first example, we're going to keep it a little bit simpler. So at first it says determine f of 3. So remember that if it's in brackets, it's talking about x. So x equals 3 in both of my functions. So I look at x equals 3. F of x is like 3. So I could write it as f of 3 is 3. And g of 3 is -2. Always double check that what your scale is, because I was inclined to say, oh, that's 1.5, but no, it's 3 based on my scale. Determine that f of 3 plus g of 3. So all that means is that I'm going to take those output values, those y values, and I'm going to add it. So g of 3, so that means I'm going to take 3 plus -2, which gives me 1. Okay, and just as a side note, that this notation means the same thing as this notation. They are one and the same. Okay, so whether you see the functions being added with a specific value or the functions being added each with individual values, they're meaning the same thing. Same goes for subtraction. So we're going to subtract g, or we're going to subtract f from g at -5. So what that means is I'm going to rewrite it just for personal preference. You don't have to do that step. Then I look at my graph. G of x at -5 is -2. Minus, if you like brackets, it helps to just consolidate everything. F of x at -2 is +5. So, and again, these running equal signs are not great to use actually in math in terms of math language. It's like a run-on sentence. But for our purposes, because we don't have a lot of workspace here, I'm going to use them. So -2 minus 5, which would be -7. What are the approximate zeros of f minus g of x? So when would they cancel out if we were subtracting? Well, they would cancel out if we were looking at intercepts. So in that case, look here and here. So I would say at x equals about negative 2.5, 2.6, and positive 1.3. You can even do that. Okay, so again, that little wavy equal sign being approximate, not exact value. Domain and range of f of x. Well, it looks like it's, if the line goes off my graph, assume that there's arrows here, okay? In which case my domain is going to be, and I'm going to use interval notation, negative infinity to positive infinity. My range is going to be, again, 0 and upward. 0 to positive infinity. Now, here is where things get tricky. What are the zeros of f times g of x? So how do we create zeros when multiplying? We do that. I'm just going to change my color here so we don't get them confused. When we have 0, so zeros of original functions is what's going to help us find zeros when we're multiplying. So we're actually going to have 3 answers. They're going to be at x equals negative 4, 0, and 2. Okay, so all of those traits can be gleaned all just by looking at the graph. So it's kind of sweet. So when we're asked to subtract full functions, you can do it visually just by choosing specific points, but you can also do it by making a table of values. The one thing you have to note is that if there's no function, we can't do the question. So because f of x only starts at 0, and I'll make a note of this, because it only starts at 0, combining these functions can't happen before one of them exists. So what does that mean? It means that we are heavily reliant on my domain. So my domains of g of x would be negative infinity to positive infinity, but f of x is restricted. It only starts at 0 and goes to positive infinity. So this is my restriction. So everything before it is no longer important. From here I can make tables of values. That'll be the strategy that I use here, just so you can see what it looks like. So what I would recommend is pause the video for a second, choose some points that you can use, and then go from there. You can always restart the video. I'm going to pause to define my points just so that, oops, what's going on here? Just so that you can try it on your own. Okay, so this is how I would set my table of values up. It's g of x and f of x, remembering that these whole pieces together represent output, or my y value. Okay, so I choose some x values that work with my domain and range, and then I find their outputs, and then I can subtract them. Note that everything in f of x is approximately their values, because I can't get the actual values from the graph. Also, I've got this question mark beside 9 because I genuinely don't know if that's what it would be, because my graph doesn't cross that line representing x equals 4. So I probably wouldn't actually use these values, which sucks because it was my only actually defined point for f of x. But I'm not going to take that risk of imagining that I've extended my graph correctly. So from here, I'm going to do what I was told in my question, f of x minus g of x. I messed up my order here, which is always why it's good to go back to your question. So 0 minus 0 is still 0. That one's nice. 0.08 minus 1 is about like negative 0.2. Minus 0 is 1.2. And subtract 4 is about negative 2.2. Okay, so those are going to be my values. So now I can graph them. I can use a different colored pen just for the sake of it showing up. So again, I'm going to do this in blue. So I've got 0 and 0. That makes sense. Negative 0.2. Nice and close there. Positive 1.5, or 1.2 rather, should be there. And then negative 2.2 just here. Now, because both of these graphs are smooth transitions, I have to make my graph look like it's a smooth transition. So it's gonna look weird, and that's okay. From here, they're diverging more and more and more. Okay, so I'm going to be subtracting bigger and bigger numbers from numbers that aren't really changing. So I can anticipate that my graph will curve downwards like this. It's tricky here. There we go, something like that. It's a messy graph, it's not pretty. I never promised that it would be. But again, noting that my domain can't extend to the left. Example 3, we're dividing, the same principle is still going to apply. So, and we're asked this time for the domain. So I'm going to color code again. So f of x, I'm going to color code g of x, and of course, my final answer. So g of x in orange, domain is going to be negative infinity to positive infinity. It looks like it's kind of restricted, but that's just because we only get that tiny little picture of a graph. There's no reason we would assume that there's an asymptote there. There's no behavior that specifically shows it. So negative infinity to positive infinity. When we look at f of x, again, we see a horizontal extension in both directions. So it would be safe to say that we should hypothetically have the same domain, but it's not fair to assume that. So before we start filling in the domain of f of x divided by g of x, we're going to do some thinking about this. So any graph is undefined when, or anything that's undefined when we're dividing by 0. And g of x is in our denominator, so actually we would expect to see that we're going to have critical points or problems when g of x equals 0, which is here. And we've got 2 spots. So right now, because they are undefined there, I'm going to assume that we've got asymptotes if my denominator is undefined. X equals negative 3 and x equals 3. Beyond that, I'm just going to have to choose points. So I've got 0 divided by 9 is 0, so that's still going to be defined. I've got 1 or negative 1 divided by positive 8 is 1/8, so it's really teeny tiny. Both of these graphs seem to be symmetrical, so I can kind of pick and choose. This looks like it's going to be approximately a half. So again, instead of using my table of values, I can also just pick points off a graph. Anything divided by itself is a 1, so oops. here, here, and we're getting this kind of like really flattened parabola. Okay, on the outsides, we're dealing with like -7 is dividing into 4. That's negative, not even 1. Again, symmetry on these graphs allows me to extrapolate those points. If I continued choosing points, like if I chose like this point here and so forth, I could define more points in amongst here, but what I would generally expect to see is this shape, similar to what we saw with reciprocals last year. So there you go. We've got some points to find. Again, I'm not going to assume any points beyond these, strictly because my graph doesn't extend that far for g of x. Once I've got it drawn, now I can state my domain very easily. I can state that I start at -infinity, and I kind of hit a roadblock at -3. But my graph picks up again on the other side of that roadblock and continues to my next roadblock. And finally, we start at 3 again and extend all the way to +infinity. If you were wanting to do this in set notation, what you would do is you would say x is an element of the reals, and x cannot be positive or -3. So whichever notation you prefer. The key thing is to be able to identify that these are asymptotes because we can't divide by 0. That's a huge restriction. And then being able to create a graph from there. So again, table of values, like we did in the previous question, would have been a totally valid option here. Choosing points, choosing x values, and discovering the y outputs for both functions, and then dividing from there. Or you can do it graphically like we did here. Okay. So we can think of asymptotes kind of like, I'm not sure if any of you live in Windsor Park or have experienced Windsor Park, but there's this road called Spears, and there's an interruption between it when it's heading to Fermor. There's the path that cuts it off, but it should connect all the way through to like the Southdale shopping. And then there's also another point where it cuts off right beside Bellevue, but then it continues on the other side of Bellevue. So that's a really good example of where we see kind of these like quote unquote roadblocks, aka asymptotes, where if you were driving your car, you wouldn't be able to actually pass through those points, but on both sides of it, you're still able to drive. The road still exists, and so does our graph. So I will post some practice questions for you here. I just want to triple check that I'm not missing any examples. Nope. I'll post some practice questions here, but we're going to be practicing for the next few lessons. So really lesson 8 is where we're going to hit a lot of heavy practice. But I hope that makes sense. Like usual, ask all the questions. I focused heavily on domain and range in my notations here because I've had a question about that. So please keep asking questions, and I can adjust my lessons accordingly to make sure that I'm meeting your needs. Otherwise, have a great day.